Tonight, we're going to explore a journey that sounds simple at first. If humanity left Earth in 2026, how long would it take to reach Alpha Centauri? There are three facts that make this question feel almost impossible to hold at once. Alpha Centauri is the nearest star system beyond our own. It sits a little more than 4 light-years away. And that means the distance between Earth and our closest stellar neighbor is roughly 25 trillion miles. Given those numbers, Alpha Centauri should feel almost reachable. It is the next star system over. It is the first place we would point to if we ever wanted to leave the solar system and aim for another sun. Yet instead, when we measure that distance against the spacecraft we can actually build, the answer stretches from decades to thousands of years to longer than recorded human history. And by the end of tonight, you're going to understand why that might mean the nearest star is still far enough away to expose the true limits of human spaceflight. Because Alpha Centauri has a strange place in the human imagination. It is far, but it is not random. It is not some nameless star buried deep in the Milky Way. It is the closest system beyond the Sun. It is the first real destination outside our own solar neighborhood. When people imagine interstellar travel, they often picture distant galaxies, strange alien skies, and ships moving easily between stars. But the first serious test is much simpler than that. It is just one nearby star system, one jump beyond the Sun, one attempt to cross the dark space between here and the closest place that could honestly be called another stellar home. And even that first step is enormous. Light itself, the fastest thing in the universe, takes more than 4 years to get there. A beam of light leaving Earth tonight would not arrive at Alpha Centauri until more than 4 years had passed on Earth. A radio message sent toward that system would crawl across space at the fastest speed nature allows and still need years to arrive. That is the easy version of the journey. For machines made by humans, the story changes completely. A spacecraft does not move like light. It must be launched. It must accelerate. It must carry power, instruments, fuel, shielding, and guidance systems. If humans are aboard, it must also carry air, water, food, warmth, medicine, and some way to keep people alive, while Earth becomes a fading point behind them. So the question is not only how far Alpha Centauri is. The question is, what happens when the closest star meets the limits of 2026 technology? If we use spacecraft that already exist, the answer becomes almost shocking. Not hundreds of years, not a few lifetimes, but thousands or even tens of thousands of years, depending on which spacecraft speed is used. A journey that sounds like the first step into interstellar space suddenly becomes a journey longer than agriculture, longer than cities, longer than written language. And this is where the contradiction begins. Alpha Centauri is our closest neighbor, but it is not close in any human sense. It is close only because the galaxy is so vast that 25 trillion miles counts as nearby. It is close only because the space between stars is so empty, so stretched out, and so much larger than the distances inside our solar system. The Moon is about 240,000 miles away. Mars, at a favorable distance, is tens of millions of miles away. Pluto is billions of miles away. These already feel like extreme destinations. Alpha Centauri is trillions of miles beyond all of that. So tonight, the journey begins with a simple question. If we left in 2026, how long would it really take? to answer it properly, we need to move carefully. We need to define the destination, measure the distance, compare real spacecraft, look at the fastest machines we have ever built, and then ask, what kind of future technology would be needed to make the trip shorter than the lifespan of a civilization? And before we can calculate the journey, we need to understand the place we are trying to reach. Because Alpha Centauri is not just one star waiting in the dark. It is a system, a small family of suns bound together by gravity, sitting at the edge of what humanity can name, measure, and dream about. Alpha Centauri sounds like the name of one star, but it is really the name of a system. 3 stars, bound together by gravity, moving through space as one nearby stellar family. The 2 brightest members are called Alpha Centauri A and Alpha Centauri B. They sit close enough together that, from Earth, they can look like a single point of light in the southern sky. To the unaided eye, they blend into one bright star. Through a telescope, they separate into 2 suns. Alpha Centauri A is the larger and brighter of the pair. It is very similar to our own star. Its mass is a little higher. Its temperature is close enough that it shines with a familiar yellow-white glow. If a person could somehow stand on a safe world nearby and look toward it, Alpha Centauri A might feel strangely familiar. A star like the one that lights Earth. Alpha Centauri B is slightly smaller, cooler, and dimmer. It glows more orange than its companion. Together, these 2 stars orbit around a shared center of gravity. They do this slowly, taking almost 80 years to complete one orbit around each other. Their distance changes as they move. At their closest, they come to about 11 times the distance between Earth and our own star. At their farthest, they spread out to about 36 times that distance. So even the central pair is wide by the standards of planets. But by the standards of stars, they are locked in an intimate dance. Then, much farther away, there is the 3rd member, Alpha Centauri C. Most people know it by another name, Proxima Centauri. Proxima is much smaller than the other 2. It is a red dwarf, which means it is a small, cool, faint star that burns its fuel very slowly. Red dwarfs are the most common stars in the galaxy. They can last for hundreds of billions or even trillions of years because they use their fuel so slowly. Proxima is only about 1/8 the mass of our own star. It is so dim that it cannot be seen with the naked eye from Earth. Even though it is the nearest star to us, it hides in the dark unless a telescope is pointed in the right direction. And Proxima is far from the bright central pair. It orbits Alpha Centauri A and B from a huge distance, taking hundreds of thousands of years to complete one slow path around them. This matters because when people talk about traveling to Alpha Centauri, the target depends on what they mean. The bright double star is slightly farther away. Proxima Centauri is the closest part of the system. It sits about 4.24 light-years from Earth. That makes Proxima the nearest known star beyond our own solar system. So for a journey asking how long it would take to reach Alpha Centauri, Proxima becomes the practical first target. It is the nearest shore across the interstellar ocean. And it is more than just a star. In 2016, astronomers announced the discovery of a planet orbiting Proxima. That planet is called Proxima Centauri b. It is thought to be at least roughly Earth-sized. It orbits inside the region where temperatures could allow liquid water, depending on its atmosphere and surface conditions. That does not mean it is comfortable. Proxima is an active red dwarf. It can release powerful flares, sudden bursts of radiation that would be dangerous for any planet close enough to receive warmth. But the existence of even one possible rocky world makes the system feel more real. Alpha Centauri is no longer just a bright name in a star catalogue. It is a nearby system with multiple stars, a possible planet, and a place in the sky that could become humanity's first true interstellar destination. Now that the destination has a shape, the distance becomes harder to ignore, because reaching Alpha Centauri does not mean reaching a vague point of light. It means crossing the space between our star and another family of stars. And that space is where the real problem begins. A light year sounds like a measure of time, but it is a measure of distance. It means the distance light travels in one full year, and light moves faster than anything else in the universe. In empty space, light travels about 186,000 miles every second. In 1 second, a beam of light could circle Earth more than 7 times. In 1 minute, it could travel about 11 million miles. In 1 day, it could cross more than 16 billion miles. And after 1 full year of moving at that speed, light has traveled almost 5.9 trillion miles. That is 1 light year. Proxima Centauri is about 4.24 light years away. So even light needs more than 4 years to travel from Earth to the nearest known star beyond our own system. A radio signal moves at the speed of light too. So if a radio message was sent toward Proxima Centauri in 2026, it would arrive more than 4 years later. If someone there could answer immediately, the reply would take more than 4 more years to return. A simple hello and response would take nearly 8.5 years. That is at the fastest speed the universe allows. The distance itself is roughly 25 trillion miles. That number is hard for the mind to hold, so it helps to shrink it down into familiar steps. The moon is about 240,000 miles from Earth. That was already far enough that the Apollo astronauts needed about 3 days to get there. Mars can come within about 35 million miles of Earth during close approaches, though the distance changes because both planets are moving around our own star. Pluto is much farther. On average, Pluto orbits about 3.7 billion miles from our own star. New Horizons launched in 2006 and reached Pluto in 2015. That was one of the fastest planetary journeys ever made. It still took more than 9 years, but compared with Alpha Centauri, Pluto is nearby. Proxima Centauri is not a little farther beyond Pluto. It is thousands of times farther. The distance from Earth to our own star is called 1 astronomical unit. That distance is about 93 million miles. Pluto sits around 39 astronomical units from our own star on average. Proxima Centauri is about 268,000 astronomical units away. That means the nearest star is not just outside the planetary region. It is far beyond the entire familiar scale of the solar system. If Earth and our own star were separated by 1 inch, Pluto would be only a few feet away. On that same scale, Alpha Centauri would be several miles away. The solar system would feel like a small room. The nearest star would be across a city. This is why the word nearest can be misleading. Nearest does not mean close. It only means nothing else is closer. Alpha Centauri is our neighbor because the galaxy is enormous. It is nearby. In the same way, a distant lighthouse can be the closest light on a dark coast. The light is visible, the direction is clear, but the water between here and there is still vast. And this distance changes the entire meaning of travel. Inside the solar system, we measure missions in months, years, or decades. A spacecraft can reach the moon in days. It can reach Mars in months. It can reach Jupiter in a few years. It can reach Pluto in under a decade if the trajectory is powerful enough. But Alpha Centauri belongs to a different scale. It is not part of the planetary neighborhood. It is the first step into the space between stars. And that space is so wide that distance alone cannot answer the question. 25 trillion miles is only half of the problem. The rest depends on speed, not the speed of imagination, not the speed of science fiction, the speed of machines that humanity can actually launch in 2026. Leaving in 2026 sounds like a launch date, but for this journey, it is more than a date. It is a limit. It means the mission begins with the technology humanity actually has. Real rockets, real engines, real spacecraft materials, real navigation systems, real power sources, real speeds that have already been demonstrated beyond Earth. That matters because Alpha Centauri can be imagined in many different ways. A science fiction ship could cross the distance quickly. A future civilization might use engines we have not built yet. A tiny laser-pushed probe might someday reach a fraction of light speed. But if the question is what happens when humanity leaves in 2026, then the first answer has to be based on machines we know how to launch. And the machines we know how to launch are still built for the solar system. They are built to reach the Moon, Mars, Jupiter, Saturn, Pluto, asteroids, comets. They are not built to cross 25 trillion miles of interstellar space. In 2026, humanity has powerful launch vehicles. A rocket can lift cargo into orbit. A spacecraft can use chemical engines to leave Earth. It can use gravity assists from planets to gain speed. It can use small thrusters to adjust its path. Some spacecraft use ion engines, which produce very gentle thrust for long periods by pushing charged particles out the back. Ion engines are efficient, but slow to accelerate. They are excellent for certain missions inside the solar system. They are not a magic shortcut to another star. This is the first hard boundary. Modern spaceflight is amazing, but it is still mostly a way of moving through the region controlled by our own star. Almost every mission humans have flown, or sent by machine, has taken place inside one small gravitational neighborhood. Even Voyager 1, the most distant human-made object, is still close compared with Alpha Centauri. It has crossed into interstellar space, but it has not come anywhere near another star. It is like a ship that has left the harbor, entered the open ocean, and still has an entire planet of water ahead of it. The difference between leaving the solar system and reaching Alpha Centauri is enormous. One is crossing a boundary. The other is crossing the space between stars. So a 2026 launch forces the script into two separate paths. The first path is proven technology. This means spacecraft that already exist, or spacecraft that could be built with known engineering. Chemical rockets, gravity assists, ion drives, nuclear power systems for electricity, careful navigation through deep space. This path gives the most honest answer. It is also the slowest answer. The second path is theoretical technology. This includes fusion drives, antimatter engines, nuclear pulse ships, laser-pushed sails. Ideas that may obey the laws of physics but do not exist as working starships. These ideas matter because they show what humanity might need to make Alpha Centauri reachable on human time scales. But they cannot be treated the same way as a spacecraft sitting on a launch pad. That is why the date matters. 2026 does not mean humanity can choose any engine it can imagine. It means humanity begins from where it actually stands. A species that has sent astronauts to the moon. A species that has landed robots on Mars. A species that has flown past every major planet. A species that has pushed a few silent machines beyond the outer boundary of the solar wind. But still, a species that has never sent anything even 1 light year from Earth. That is the quiet truth behind the whole journey. The nearest star is not waiting for one better rocket. It is waiting for a completely different level of motion. And to see how large the gap really is, the most honest place to begin is with the spacecraft already traveling outward through the darkness beyond the planets. The spacecraft already traveling outward is Voyager 1. It is the natural place to begin. Voyager 1 launched from Cape Canaveral, Florida on September 5, 1977. It was carried into space on a Titan IIIe rocket. At launch, the spacecraft weighed about 1,820 pounds. That is less than the weight of a small car. It was built for a mission to Jupiter and Saturn, not another star. Not Alpha Centauri, not the deep future, just the outer planets. And yet, almost half a century later, Voyager 1 has become the most distant human-made object ever sent into space. It flew past Jupiter in 1979. It flew past Saturn in 1980. Then Saturn's gravity bent its path upward, away from the flat plane where most of the planets orbit. From there, Voyager 1 began its long escape from the planetary region. In 2012, it crossed the heliopause. That is the boundary where the solar wind from our own star gives way to the thin gas and magnetic field between the stars. It became the first spacecraft to enter interstellar space. That phrase sounds enormous, and it is. But it can also be misleading. Interstellar space does not mean Voyager 1 is near another star. It only means it has moved outside the main bubble of particles, blown outward by our own star. It has left the harbor. It has not crossed the ocean. Voyager 1 is now more than 15 billion miles from Earth. That is so far away that radio signals take more than 22 hours to travel from the spacecraft back to us. A command sent from Earth takes almost a full day to reach it. Then the reply takes almost a full day to come back. A simple exchange with Voyager 1 can take close to 2 days. And still, after all that distance, Voyager 1 has covered only a tiny fraction of the distance to Alpha Centauri. The spacecraft is moving at roughly 38,000 miles per hour relative to our own star. That is fast by any earthly standard. At that speed, it could cross the distance from New York to Los Angeles in only a few minutes. It could circle Earth in less than an hour. It could pass the moon's distance in less than a day. But Alpha Centauri is not across a continent. It is not across the moon's orbit. It is not even across the known planetary region. It is about 25 trillion miles away. If Voyager 1 was somehow aimed directly at Proxima Centauri, it would need roughly 70,000 to 80,000 years to get there. A common estimate is about 75,000 years. That number is almost hard to feel because it is longer than the oldest cities, longer than written language, longer than agriculture, longer than the entire span between the first permanent villages and the modern world. Farming began around 10,000 to 12,000 years ago. The first cities appeared only several thousand years after that. The earliest known writing systems emerged roughly 5,000 years ago. Voyager speed would turn a trip to the nearest star into a journey lasting many times longer than civilization itself. If a spacecraft left Earth in 2026 at Voyager speed, no living person would see it arrive. No child born that year would see it arrive. No nation on Earth could reasonably expect to still exist in the same form when it arrived. Languages would change. Coastlines would shift. Ice ages could come and go. Entire cultures could rise, disappear, and be forgotten. And the spacecraft would still be traveling. This is the first honest answer. With one of humanity's most famous deep space machines, Alpha Centauri is not a destination measured in years. It is measured in epochs. Voyager 1 shows that reaching interstellar space and reaching another star are completely different achievements. The first can happen within a human lifetime. The second, at Voyager speed, belongs to a future so distant it starts to feel geological. But Voyager 1 was built in the 1970s. Its computers have less memory than a simple modern device. Its mission was designed before the internet age, before smartphones, before almost every technology people now carry in their pockets. So maybe the answer improves when we look at a newer spacecraft, a faster mission, a probe that crossed the solar system in the 21st century and reached Pluto in less than a decade. The newer comparison is New Horizons. It is one of the clearest examples of fast, modern planetary travel. New Horizons launched on January 19, 2006. It left Earth aboard an Atlas V rocket from Cape Canaveral, Florida. At launch, it became one of the fastest spacecraft ever sent away from Earth. Its speed, after leaving our planet, was about 36,000 miles per hour. That is fast enough to cross the distance from Earth to the Moon in less than 7 hours. For a mission inside the solar system, that kind of speed is extraordinary. New Horizons did not slowly crawl outward. It raced. In February of 2007, it passed Jupiter. Jupiter's gravity gave it a boost, bending its path and adding speed without using extra fuel. That gravity assist saved years of travel time. Without Jupiter, the journey to Pluto would have taken much longer. Then, for more than 8 years, New Horizons crossed the outer solar system. It passed the orbit of Saturn, then Uranus, then Neptune, and on July 14, 2015, it finally swept past Pluto. The flyby happened about 7,800 miles above Pluto's surface. That was close enough to reveal mountains made of water ice, smooth plains of frozen nitrogen, a thin blue haze in Pluto's atmosphere, and a bright heart-shaped region, now known as Tumbor Regio, named after Clyde Tumbor, the astronomer who discovered Pluto in 1930. The whole journey took about 9.5 years. For a spacecraft mission, that felt fast. Pluto had once seemed like the distant edge of the known planetary world. New Horizons crossed that distance in less than a decade. It gave humanity its first close look at a frozen world more than 3 billion miles from our own star. But Alpha Centauri changes what fast means. Pluto is far. Alpha Centauri is in a different category. Pluto orbits at an average distance of about 3.7 billion miles from our own star. Proxima Centauri is about 25 trillion miles away. That makes the nearest star more than 6,000 times farther than Pluto's average distance from the center of the solar system. So, a speed that looks spectacular on the way to Pluto becomes painfully small when stretched across interstellar space. If New Horizons were aimed toward Alpha Centauri at roughly its early mission speed, the journey would still take around 70,000 to 80,000 years. Using some estimates of its later speed, the number can become even longer. The exact answer depends on which speed is used, but the conclusion stays the same. New Horizons does not turn Alpha Centauri into a human-scale destination. It only confirms the same hard pattern. Inside the solar system, modern spacecraft can seem astonishingly fast. Across the distance to another star, they are almost still. This is why planetary travel can be misleading. A spacecraft can cross billions of miles and still be nowhere close to crossing a light year. New Horizons reached Pluto in the time between a child entering elementary school and that same child entering high school. But if that same speed were used for Alpha Centauri, the journey would last longer than the time between the first cave paintings and the present day. It would outlast nearly every trace of the society that launched it. The spacecraft would leave in 2026. It would continue through the rise and fall of languages, governments, cities, coastlines, and climates. It would travel through the silent dark, while Earth changed behind it. And after all of that, it would still be following a path toward the nearest known star. New Horizons teaches the same lesson as Voyager, but in a sharper way. Even a fast 21st century probe, launched with powerful rockets and helped by Jupiter's gravity, still cannot make Alpha Centauri feel close. The distance is too large, the speed is too small, and the gap between them is the entire problem. But there is one spacecraft whose speed seems to break this pattern. A machine built to fall closer to our own star than any spacecraft before it. A machine that can reach speeds so high that, for a moment, the numbers begin to sound different. The spacecraft that seems to change the answer is Parker's solar probe. It launched on August 12, 2018. Its mission was not to leave the solar system. Its mission was to study our own star up close, closer than any spacecraft had ever gone before. Parker's solar probe was built to fly through the outer atmosphere of the Sun, a region called the corona. The corona is the thin, extremely hot layer of plasma that surrounds our own star. Plasma is gas so hot that atoms are stripped apart into charged particles. Near Earth, the corona is visible during a total solar eclipse as a ghostly white glow around the darkened disk. Parker was sent directly into that dangerous region. To survive, it carries a heat shield made from carbon composite material. The shield is only a few inches thick, but it protects the instruments behind it from temperatures that can reach thousands of degrees. The spacecraft must keep that shield pointed correctly at all times. A small pointing mistake near the Sun could expose delicate equipment to heat intense enough to destroy the mission. But the same close approach that makes Parker dangerous also makes it fast. Parker's solar probe does not reach its record speed by using one giant engine. It reaches that speed by falling deep into the gravity well of our own star. A gravity well is the invisible slope created by a massive object. The closer a spacecraft falls toward a massive body, the faster gravity pulls it along. Earth creates a gravity well. Jupiter creates a much deeper one. The Sun creates the deepest gravity well in the solar system. Parker uses that gravity again and again. It also uses repeated flybys of Venus to shrink its orbit. Each Venus flyby changes the shape of Parker's path, allowing it to swing closer to our own star on later passes. The orbit becomes long and stretched out. Farther away, Parker moves more slowly. Near closest approach, it whips around our own star at incredible speed. That closest point is called perihelion. It simply means the closest part of an orbit around the Sun, though for this script, it is safer to think of it as the moment Parker dives deepest toward the center of the solar system. At its fastest, Parker's solar probe reaches about 430,000 miles per hour. That is about 687,000 kilometers per hour. It is the fastest speed ever reached by a human-made object. At that speed, Parker could travel from New York to Los Angeles in less than 30 seconds. It could cross the distance to the Moon in well under an hour. It could circle Earth many times in a single afternoon. Compared with Voyager 1 or New Horizons, the number feels almost unreal. Voyager 1 moves at roughly 38,000 miles per hour relative to our own star. Parker's peak speed is more than 10 times higher. For a moment, it sounds like the Alpha Centauri problem has changed. Maybe the nearest star is no longer a 70,000-year journey. Maybe the fastest spacecraft ever built gives a better answer. But Parker's speed is not a simple cruising speed. It is not moving in a straight line toward another star. It is racing around the Sun in a special orbit, gaining speed as it falls inward, then moving outward again. The record number belongs to a particular moment in that orbit. It is not the same as pointing Parker at Alpha Centauri and keeping that speed for 25 trillion miles. This distinction matters. A spacecraft can be incredibly fast near a massive object and still be poorly suited for interstellar travel. Parker is like a stone swinging at high speed around the end of a string. At the closest part of the swing, the motion is violent and fast, but that does not mean the stone is flying straight across an ocean. Parker's solar probe is one of the most impressive machines humanity has ever launched. It survives heat, radiation, and gravity in a place no spacecraft had ever explored so closely. It teaches us about solar wind, magnetic fields, and the violent behavior of our own star. But it was not designed to cross interstellar space. Its speed is real. Its record is real. The temptation is real too. Because even if Parker cannot simply be turned toward Alpha Centauri, the number is too important to ignore. What would happen if a spacecraft could somehow carry Parker like speed across the dark gap between stars? So let us take Parker Solar Probe's record speed seriously. 430,000 miles per hour. A number so large that it barely fits normal experience. At that speed, a spacecraft would travel more than 10 million miles in a single day. In 1 week, it would cross more than 70 million miles. In 1 year, it would cover almost 3.8 billion miles. That is roughly the average distance from our own star to Pluto. So on the scale of the solar system, Parker's speed is extraordinary. A trip that would take ordinary spacecraft many years can be compressed into something that feels almost sudden. A machine moving that fast could cross the inner solar system with shocking speed. It could pass Earth's orbit, then Mars, then the asteroid belt, then Jupiter's orbit, and it would still feel like it was moving through familiar space quickly. But Alpha Centauri is where the number changes shape. The nearest part of the Alpha Centauri system is about 25 trillion miles away. If a spacecraft could somehow move toward it at 430,000 miles per hour, without slowing down, without drifting off course, and without needing to loop around our own star, the travel time would still be about 6,600 years. That is the generous version. The version where the fastest speed ever reached by a human-made object is treated like a steady cruising speed across interstellar space. And even then, the answer is thousands of years. A launch in 2026 would arrive around the year 8,600. That date is so far away that it stops feeling like planning. It becomes deep history in reverse. Think about what 6,600 years means. 6,600 years ago, much of human civilization was still forming. Farming had spread through parts of the world, but many societies were still living in small villages. Large cities were rare. Writing had barely begun, or had not yet appeared in many places. The pyramids of Egypt had not been built yet. The Roman Empire was thousands of years away. Electricity, telescopes, rockets, satellites, and computers were unimaginably far in the future. That is the span of time Parker's speed would need to reach the closest known star. So the fastest human-made object does improve the answer. It changes the journey from something like 70,000 years to something closer to 6,000 or 7,000 years. That is a huge difference. It is the difference between a journey longer than modern humanity's entire cultural memory and a journey about as long as recorded civilization itself. But it still does not create a practical mission. No government can plan around 6,600 years. No science team can wait that long for data. No spacecraft electronics have ever operated across that kind of time. Voyager 1 has lasted almost half a century, and that is already one of the greatest engineering achievements in space history. 6,600 years is more than 100 times longer than that. A spacecraft would need power systems that last for millennia, computers that survive radiation and cold for thousands of years, materials that can endure dust impacts, temperature changes, and slow damage from cosmic rays. It would need a way to stay pointed, stay awake, and stay understandable to whatever civilization exists when it arrives. The mission would also face a deeper problem. Parker's solar probe's record speed comes from falling close to our own star. It is a peak speed near the closest part of its orbit. To use that number for Alpha Centauri, we are pretending a spacecraft could take that moment of speed and carry it straight outward forever. That is useful for comparison. It is useful for feeling the scale, but it is still a generous thought experiment. The real spacecraft would need a trajectory, a source of energy, a way to aim, a way to survive, a way to communicate. And if it wanted to do more than fly past the Alpha Centauri system, it would eventually need a way to slow down. That is why the best modern speed estimate is so humbling. Even when humanity's fastest machine is given the most favorable treatment, the nearest star remains beyond normal historical time. The problem is no longer just the highest speed we have ever reached. It is whether any spacecraft can carry that speed across 25 trillion miles of dark, thin, silent space. Speed in space is stranger than speed on Earth. On Earth, a fast vehicle usually moves along a clear path. A car drives down a road. A plane crosses the sky. A train follows a track. But spacecraft do not simply point forward and keep going in a straight line. Most of the time, they are falling. They are falling around planets, falling around our own star, falling through gravity fields that bend their paths and change their speeds. That is why spacecraft speed records can be misleading. A probe can be moving incredibly fast at one moment while still being trapped in an orbit that brings it back around again. Parker Solar Probe is the clearest example. Its speed is real. Its record is real. But that speed comes from a deep dive toward the center of the solar system. It is not a steady cruise toward Alpha Centauri. Voyager 1 gives a different example. Voyager did not leave the solar system because its engines kept firing for decades. It used gravity assists. A gravity assist is when a spacecraft passes near a planet and steals a tiny amount of that planet's orbital motion. The planet loses an amount of speed too small to notice. The spacecraft gains enough speed to change its entire future. Voyager 1 used Jupiter in 1979. Then it used Saturn in 1980. Those encounters bent its path and helped send it outward for good. New Horizons used the same basic trick. It launched in 2006. Then it passed Jupiter in 2007. Jupiter's gravity boosted the spacecraft and shortened its trip to Pluto by several years. Without that assist, the Pluto flyby in 2015 would have taken much longer. These maneuvers are brilliant. They are one of the reasons robotic space exploration has worked so well, but they also reveal a limitation. The fastest spacecraft are often fast because they were in the right place at the right time, near a powerful gravitational body. Their speed comes from the architecture of the solar system. A planet, a close solar pass, a carefully shaped orbit. Alpha Centauri does not offer that help at the start. Once a spacecraft leaves the planetary region, there are no giant planets waiting every few years to slingshot it forward. There is no nearby massive object to keep feeding its speed. There is only the long, thin darkness between stars. That darkness is not completely empty. It contains scattered hydrogen atoms, tiny dust grains, magnetic fields, cosmic rays. But it does not contain anything useful for easy acceleration. A spacecraft crossing that space needs to bring its speed with it, and that changes the problem. To reach Alpha Centauri, a spacecraft needs more than a record number. It needs useful velocity. Velocity means speed in a specific direction. That direction has to be aimed toward where Alpha Centauri will be in the future, not where it appears in the sky right now. The light from Proxima Centauri takes more than 4 years to reach Earth. So when we look at it, we see where it was more than 4 years ago. The star is moving. Our own star is moving too. Both systems are orbiting through the Milky Way. A spacecraft would need to aim for a future position, like leading a moving target across a distance of 25 trillion miles. A tiny error near Earth could become an enormous miss later. Even a small drift in direction stretched across thousands of years or light years could carry the spacecraft far away from the target system. So, an interstellar probe needs navigation. It needs star trackers. It needs computers. It needs the ability to correct its course. It needs power for instruments, heaters, transmitters, and communication systems. And it needs those systems to keep working through cold, radiation, and time. This is why speed records are only the beginning. A spacecraft that is fast for 1 hour near our own star is not the same as a spacecraft that can survive for thousands of years between stars. A spacecraft that uses Jupiter for a boost is not the same as a spacecraft that can carry its own momentum across the interstellar gap. A mission to Alpha Centauri cannot be built from one impressive number. It needs direction. It needs endurance. It needs power. It needs control. And once speed has to be sustained instead of briefly reached, the journey becomes something deeper and harder. It becomes an energy problem. To cross the distance to Alpha Centauri, speed is only part of the story. The deeper problem is energy. A spacecraft does not become fast for free. Every mile per hour has to be paid for with energy. And the faster the spacecraft needs to move, the more severe the price becomes. This is because motion stores energy. The energy of motion is called kinetic energy. Kinetic simply means movement. A slow-moving object has a little kinetic energy. A fast-moving object has much more. But the relationship is not gentle. If a spacecraft moves twice as fast, it does not need twice as much kinetic energy. It needs 4 times as much. If it moves 10 times as fast, it needs 100 times as much. That is why a small increase in interstellar speed can become a huge increase in required energy. Voyager 1 is already fast by human standards. New Horizons was fast by planetary mission standards. Parker Solar Probe is extremely fast by spacecraft standards. But Alpha Centauri does not ask for ordinary spacecraft speed. It asks for a completely different level of motion. At Voyager-like speed, the journey takes tens of thousands of years. At Parker-like speed, it still takes thousands of years. To make the journey fit inside a human life, the spacecraft has to move at a meaningful fraction of light speed. Even 10% of light speed would mean about 67 million miles per hour. That is more than 150 times faster than Parker Solar Probe's record speed. And because kinetic energy grows so sharply with speed, the energy needed is far more than 150 times greater. This is where mass becomes the enemy. A spacecraft is not just a point moving through space. It has weight. It has structure. It has instruments. It has antennas. It has power systems. It has shielding. It has guidance, computers. Every piece of it has to be accelerated. A tiny probe is one kind of problem. A robotic spacecraft, the size of a car, is a larger problem. A human ship is something else entirely. A probe weighing only a few grams can be pushed to high speed in some future concepts because there is so little mass to move. A spacecraft weighing 1 ton needs vastly more energy. A crewed ship weighing thousands of tons becomes a mountain that must be thrown toward another star. The distance to Alpha Centauri makes every kilogram matter. 1 extra kilogram does not sound like much. It is about the mass of a full bottle of water. But that kilogram still has to be accelerated across interstellar space. If the spacecraft needs to reach 10% of light speed, that kilogram becomes expensive. If the mission needs shielding against radiation and dust, each extra layer adds mass. If it needs a larger antenna to send data back to Earth, that antenna adds mass. If it needs more power, the power system adds mass. If it needs spare parts, they add mass. And if humans are aboard, the mass grows quickly. People need air, water, food, temperature control, waste recycling, sleeping space, medical equipment, radiation protection, exercise equipment. A spacecraft carrying humans to Alpha Centauri would need to be more than a vehicle. It would need to be a sealed environment that can stay alive for decades, centuries, or longer. That kind of ship cannot be light. And because it cannot be light, it becomes harder to accelerate. The energy wall rises higher. This is why interstellar travel is so unforgiving. The fastest mission is usually the smallest mission. The most useful mission is usually heavier. A tiny probe might reach the system quickly, but carry only a few instruments. A larger probe might do better science, but take more energy to accelerate. A human mission might be the most meaningful, but it becomes the hardest version of the problem. Alpha Centauri forces every mission design into a trade. Speed against mass. Mass against power. Power against fuel. Fuel against more mass. And once fuel enters the picture, the problem becomes even more severe, because a spacecraft that carries its own fuel must accelerate the fuel too. The more fuel it carries, the heavier it becomes. The heavier it becomes, the more fuel it needs. And that is the oldest trap in spaceflight. The oldest trap in spaceflight has a simple shape. A rocket needs propellant to move. Propellant means the material the rocket throws backward so the spacecraft can move forward. For a chemical rocket, that usually means fuel and oxidizer. Fuel releases energy. Oxidizer supplies the oxygen needed for burning because space has no air to feed the flame. This is how rockets climb away from Earth. They burn enormous amounts of propellant. Hot gas blasts out of the engine. The rocket moves in the opposite direction. It is powerful. It is proven. It is the reason humans reached orbit, the moon, and the planets. But the same system becomes painful when the destination is Alpha Centauri. The problem was described clearly by Russian scientist Konstantin Tsiolkovsky in the early 20th century. His rocket equation shows how a rocket's final speed depends on two things: how fast its exhaust leaves the engine, and how much of the rocket's starting mass is propellant. That second part is the trap. If a rocket wants to go faster, it needs more propellant, but propellant has mass. So the rocket must also accelerate the extra propellant it is carrying. That requires even more propellant. Then that extra propellant has mass too. So the problem feeds on itself. A rocket becomes heavier because it needs fuel. Then it needs more fuel because it is heavier. This is manageable for reaching orbit. It is difficult for reaching the moon. It is carefully planned for missions to Mars, Jupiter, Saturn, or Pluto. But for Alpha Centauri, the numbers become brutal. A chemical rocket can produce enormous thrust for a short time. That is why it is useful for launch. It can lift a spacecraft through Earth's atmosphere. It can fight gravity. It can push a payload into orbit. But chemical fuel does not contain enough energy to accelerate a useful spacecraft to a meaningful fraction of light speed. The best chemical rockets throw exhaust out at only a few miles per second. That is impressive near Earth. It is tiny beside the speeds needed for interstellar travel. To reach Alpha Centauri in a human lifetime, a spacecraft would need to move at tens of millions of miles per hour. A chemical rocket would need a ridiculous amount of propellant to reach that speed. The propellant mass would grow faster than the useful spacecraft. Soon, almost everything would be fuel. Then more fuel would be needed to move that fuel. The mission collapses under its own mass. This becomes even worse if the spacecraft needs to slow down. A simple flyby can keep moving. It can race past the target and continue into deep space. But if the mission is supposed to arrive at Alpha Centauri, enter orbit, study planets, or stay there, it must remove its speed. That means braking. And braking takes energy too. In many cases, slowing down can be nearly as hard as speeding up. So the spacecraft may need propellant for the launch phase, propellant for the cruise corrections, and propellant for the braking phase at the destination. That propellant must be carried from the beginning, which makes the launch vehicle heavier, which demands more propellant again. This is why ordinary rockets cannot simply be made bigger until they reach the stars. Bigger helps for some missions, but after a point, bigger becomes the problem. A chemical rocket is like a torch, bright, powerful, violent, short-lived. It can throw a machine away from Earth. It can start a journey across the solar system. But Alpha Centauri needs something more like an engine that can change the rules of the journey itself. More energy per kilogram, more efficiency, more endurance, a way to move faster without burying the spacecraft under impossible amounts of propellant. Chemical rockets gave humanity the space age. They lifted the first satellites. They carried Apollo astronauts to the moon. They launched Voyager, New Horizons, and the probes that mapped the outer planets. But they are not the answer to a 25 trillion-mile crossing. They are the beginning of the problem. To make Alpha Centauri practical, the script has to move beyond the engines that built the first space age. It has to enter the world of nuclear propulsion. Beyond chemical rockets, the first serious leap is nuclear propulsion. The reason is simple. Nuclear reactions release far more energy than chemical reactions. A chemical rocket gets energy by rearranging atoms. A nuclear system gets energy from the center of the atom itself. That difference is enormous. In a nuclear thermal rocket, a reactor heats a lightweight propellant, usually hydrogen. The hydrogen becomes extremely hot. Then it blasts out through a nozzle, pushing the spacecraft forward. The rocket is still throwing material backward, but the reactor can heat that material more efficiently than chemical combustion can. This means a nuclear thermal engine could, in principle, get more motion from the same amount of propellant. NASA and the United States Atomic Energy Commission studied this seriously during the Cold War. One of the major programs was called NERVA. It began in the 1960s. Engineers tested nuclear rocket reactors on the ground in Nevada. Some of those test engines ran successfully. They proved that the basic idea could work. A reactor could heat hydrogen. The hydrogen could produce thrust. A nuclear rocket could be more efficient than a chemical rocket. But the program ended in the early 1970s before any nuclear rocket flew in space. The reasons were practical and political. Budgets changed. Mission priorities changed. The Apollo era was ending, and launching nuclear reactors into space created obvious safety concerns. Even if the reactor was designed to stay inactive until it reached orbit, people still worried about accidents during launch. A rocket can explode. A payload can fall back through the atmosphere. A nuclear system raises the stakes of every failure. Nuclear electric propulsion takes a different approach. Instead of using the reactor as a direct rocket engine, the reactor generates electricity. That electricity powers an engine, such as an ion drive. An ion drive works by giving electric charge to atoms, then pushing those charged atoms out of the spacecraft at very high speed. The thrust is gentle, almost like a steady whisper instead of a blast, but it can continue for months or years. This is useful for deep space missions because steady thrust can slowly build up speed over time. A nuclear electric spacecraft could operate far from our own star, where solar panels become weak. It could power instruments, communication systems, and engines for long periods. For missions to the outer planets, the Kuiper Belt, or the distant edge of the solar system, this kind of propulsion could be powerful. But Alpha Centauri is still much farther. A nuclear thermal rocket may be better than a chemical rocket. A nuclear electric system may be efficient for long missions, but neither one automatically turns 25 trillion miles into a short journey. The scale is too large. The speed requirement is too extreme. There is an even more dramatic nuclear idea: Project Orion. This concept was studied in the late 1950s and early 1960s. The idea sounds almost unreal. A spacecraft would carry many nuclear explosives. It would release them one at a time behind the ship. Each explosion would push against a massive metal plate. Shock absorbers would smooth the force. The ship would ride a series of nuclear blasts through space. On paper, Project Orion offered huge thrust. It could move very large spacecraft. Some designs imagined ships weighing thousands or even millions of tons. That made it different from delicate probes. It was one of the few concepts that seemed powerful enough to push something truly massive through deep space. But the problems were enormous. The spacecraft would need to survive repeated nuclear detonations. The pusher plate would face intense heat, radiation, and mechanical stress. The crew would need heavy shielding. The ship would need to carry a large supply of nuclear devices, and launching such a vehicle from Earth would be dangerous in a way no ordinary rocket launch could be. There were also political barriers. In 1963, the Partial Test Ban Treaty restricted nuclear explosions in the atmosphere, underwater, and in outer space. That did not erase every possible nuclear propulsion idea, but it made a Project Orion-style mission much harder to imagine in practice. Nuclear propulsion shows the first real escalation beyond chemical rockets. It gives more energy, more endurance, more possible speed. It opens a door that chemical fuel cannot open on its own. But it also brings mass, shielding, heat, radiation, safety risk, and political weight. And even with nuclear power, Alpha Centauri remains distant enough to demand an engine closer to the heart of the stars themselves. Fusion is the engine inside stars. It is the process that makes starlight possible. Deep inside our own star, hydrogen nuclei are pressed together under enormous heat and pressure. When they combine, they form helium. A tiny amount of mass is converted into energy. That energy slowly works its way outward and eventually leaves as sunlight. Every warm day on Earth begins with fusion in the core of our own star. That is why fusion feels so powerful as a dream for interstellar travel. It is not chemical burning. It is not simply heating propellant with a reactor. It is the same basic process that powers the stars themselves. If a spacecraft could carry a working fusion engine, it could use fuel far more efficiently than a chemical rocket. The most common fusion fuel ideas involve light atoms. Hydrogen isotopes are often discussed. An isotope is a version of an element with a different number of neutrons in its nucleus. Deuterium is a form of hydrogen with one proton and one neutron. Tritium is a form of hydrogen with one proton and two neutrons. When deuterium and tritium fuse, they release a large amount of energy. This reaction is one of the easiest fusion reactions to start, which is why it is studied so often on Earth. Fusion could, in principle, give a spacecraft the kind of sustained power that star travel demands. A fusion ship might accelerate for a long time. It might build speed gradually across months or years. It might reach a meaningful fraction of light speed. And unlike a tiny light sail, it could potentially carry a real payload. In the 1970s, the British Interplanetary Society studied a famous design called Project Daedalus. The idea was to send an uncrewed fusion probe to Barnard's star, a nearby red dwarf about 6 light-years away. The proposed spacecraft would use tiny fusion fuel pellets. Powerful beams would ignite those pellets one after another. Each small fusion burst would push the spacecraft forward. The design was enormous. It imagined a spacecraft weighing thousands of tons. It would not carry humans. It would be built in space, and even then, the mission would take decades. Later, in the 1980s and 1990s, a follow-up study called Project Icarus revisited the idea with newer assumptions. Both projects showed the same basic truth. Fusion makes interstellar travel feel more physically possible, but it does not make it easy. The problem is that controlled fusion is still one of the hardest engineering challenges on Earth. Scientists have been working on fusion power for more than 70 years. The goal is to make fusion happen in a controlled way, where the reaction produces more useful energy than it takes to keep it going. To do that, the fuel must become plasma. Plasma is a super hot state of matter, where atoms are stripped into charged particles. This plasma can reach temperatures of tens or even hundreds of millions of degrees. No normal container can hold it. So engineers use powerful magnetic fields or extremely brief bursts of laser compression to control it. On Earth, fusion machines are huge. They require strong magnets, complex cooling systems, precision instruments, massive power supplies, careful protection from radiation. Now imagine shrinking that challenge into a spacecraft engine. The engine would need to ignite fusion again and again. It would need to direct the energy into thrust. It would need to reject waste heat into space. It would need to operate reliably for years. And it would need to do all of this while moving far from Earth, with no repair crew waiting nearby. That is a much harder step than making fusion work in a laboratory or a power plant. A fusion-powered starship also needs fuel. Deuterium can be found in water, though only in small amounts. Tritium is radioactive and rare, so it usually has to be produced. Other fusion fuels exist, but many require even higher temperatures or more difficult reactions. So even the dream engine carries practical limits. Fusion is the first propulsion idea that starts to feel worthy of Alpha Centauri. It offers more power than chemical rockets, more promise than basic nuclear systems, more hope for reaching another star in less than geological time. But the closer the mission gets to human scale, the more extreme the demand becomes. Fusion points toward the dream. The next idea pushes even farther toward the most concentrated fuel source physics allows. Antimatter sounds like science fiction, but it is real physics. For every ordinary particle of matter, there can be an opposite particle. An electron has an antimatter partner called a positron. A proton has an antimatter partner called an antiproton. These particles have the same mass as their ordinary versions, but opposite electric charge. When matter and antimatter meet, they destroy each other. The word for this is annihilation. It means both particles vanish as particles, and their mass becomes energy. This is what makes antimatter so tempting for interstellar travel. Chemical rockets only release energy from the bonds between atoms. Nuclear fission releases energy by splitting heavy atoms. Fusion releases energy by joining light atoms. Matter and antimatter annihilation goes deeper. It converts mass itself into energy with extraordinary efficiency. Einstein's famous equation says energy equals mass times the speed of light squared. That means even a small amount of mass contains a stunning amount of energy. 1 gram of matter meeting 1 gram of antimatter could release energy comparable to a large conventional explosion. 1 kilogram of antimatter, reacting with 1 kilogram of matter, would release energy far beyond anything chemical fuel could provide. In principle, this is the most concentrated fuel source known. For a journey to Alpha Centauri, that matters. A spacecraft trying to reach a meaningful fraction of light speed needs immense energy. Fusion begins to approach that level. Antimatter pushes even farther. A well-designed antimatter engine might use the energy from annihilation to heat propellant, produce charged particles, or drive a powerful beam of exhaust. The exhaust could leave the spacecraft at extremely high speed. That is valuable because rocket performance depends partly on how fast material is thrown backward. The faster the exhaust, the less propellant is needed for the same change in speed. In theory, an antimatter-powered spacecraft could reach speeds that make nearby stars feel less impossible. Not easy, not routine, but less trapped in the tens of thousands of years we saw with Voyager and New Horizons. This is why antimatter often appears in serious discussions of advanced propulsion. It is not magic. It follows known physics. Particle accelerators already produce antimatter. Hospitals use positrons in a medical imaging method called positron emission tomography. That is the scan people often call a PET scan. So, antimatter is not imaginary. The problem is scale. Humanity can make antimatter only in tiny amounts. Particle accelerators produce it atom by atom at enormous cost and low efficiency. The total amount ever produced by humans is incredibly small, far too small to fuel a starship, and making antimatter is only the first problem. The second problem is storage. Antimatter cannot touch ordinary matter. If it touches the wall of a tank, or a speck of dust, or a bit of gas, it annihilates. So it cannot be stored in a normal container. It has to be held away from matter, using magnetic or electric fields. Charged antimatter particles can be trapped this way in laboratory devices. But a starship would need a storage system that can hold vastly more antimatter for years, decades, or longer. It would need to remain stable through launch vibration, through acceleration, through radiation, through temperature changes, through every possible failure mode. A tiny leak would not be like a fuel drip. It would be an energetic event. A larger failure could destroy the spacecraft. And there is another difficulty. Some useful antimatter forms are charged and can be held with magnetic fields. Neutral antimatter, such as antihydrogen, is harder to confine because it does not respond to electromagnetic traps in the same simple way. So even the storage physics becomes complicated. Then there is the question of how to turn annihilation into controlled thrust. Energy released in the wrong form is hard to use. Some reactions produce gamma rays, which are extremely energetic light. Gamma rays are difficult to reflect, direct, or contain. They can pass through materials and damage electronics or living tissue. A useful engine would need to manage that radiation, protect the spacecraft, and convert as much energy as possible into motion. So antimatter gives the dream of extreme speed, but it also gives extreme fragility, extreme cost, extreme danger, extreme engineering demands. It shows how desperate the Alpha Centauri problem really is. To make the nearest star reachable, we are pushed toward the edge of known physics. And after all that, the most practical shortcut may come from a stranger idea. Do not carry the fuel. Leave the power system closer to home and push the spacecraft with light. After antimatter, the next idea feels almost gentle. Do not carry most of the fuel. Do not build a giant engine. Do not place the main power source on the spacecraft at all. Instead, leave the power closer to Earth. Then push the spacecraft with light. This is the basic idea behind a light sail. Light has momentum. A photon has no ordinary mass, but it can still push. The push is tiny. When sunlight hits a surface, it applies pressure. On Earth, that pressure is far too weak to feel. But in space, with no air resistance, a very large and very light sail can slowly gain speed from light alone. The idea has already been tested in smaller ways. Japan's Icarus spacecraft used sunlight to sail through space after launching in 2010. The Planetary Society's Light Sail 2 mission also demonstrated controlled solar sailing in Earth orbit after launching in 2019. These missions were not starships. They were proof that light can push a spacecraft in a measurable way. But sunlight alone is too weak for a fast trip to Alpha Centauri. The farther a sail moves from our own star, the weaker the sunlight becomes. By the time it reaches the outer solar system, the push is faint. By interstellar distances, it is almost gone. So the Alpha Centauri version uses something stronger, a powerful beam of light. Not sunlight spreading naturally in all directions. A focused beam aimed at a tiny reflective sail. This is the idea behind Breakthrough Starshot, announced in 2016. The concept is not to send a large spacecraft. It is to send extremely small probes. Sometimes they are described as nanocrafts. Each one could be only a few grams. The electronics might fit on something closer to the size of a small chip. The sail might be only a few meters across. The probe would be placed near Earth. Then a huge array of powerful lasers or other light sources would aim at the sail. For a short time, the beam would strike the sail and push it forward. The acceleration would be extreme. In some versions of the concept, the probe could reach about 20% of the speed of light. That is roughly 134 million miles per hour. A more rounded version often says up to about 100 million miles per hour. At that speed, Alpha Centauri would no longer be 75,000 years away. It would no longer be 6,600 years away. It could be reached in just over 20 years. For the first time, the number fits inside a human life. A person could be alive when the probe launches, and still be alive when it passes through the Alpha Centauri system. Then the data would need to come home. Because Alpha Centauri is more than 4 light years away, any signal from the probe would still take more than 4 years to return to Earth. So the whole experience might be closer to a few decades. Launch the probe. Wait about 20 years for the flyby. Then wait more than 4 years for the first signals to arrive. That is still long. But it is not ancient history. It is not longer than civilization. It is not a spacecraft leaving and arriving in a world completely beyond recognition. This is why light sails are so important. They change the timeline, but they do it by changing the spacecraft. A light sail probe to Alpha Centauri would not be a ship. It would not carry people. It would not carry a laboratory the size of a room. It would not carry heavy cameras, large antennas, thick shielding, fuel tanks, or landing systems. It would be tiny. Fast, because it is tiny. Possible because it is tiny. And limited for the same reason. The shortcut works by removing mass until the spacecraft becomes almost unbelievably small. So the 20-year answer is real in a very specific sense. Something might be able to get there quickly. But what kind of mission does that actually buy? A light sail probe gives the first answer that feels close to human time. But it also creates a strange problem. It may reach Alpha Centauri too fast to stay there. If a tiny probe travels at about 20% of the speed of light, it is moving at roughly 134 million miles per hour. That is about 37,000 miles every second. At that speed, the probe could cross the distance from Earth to the Moon in only a few seconds. It could cross the width of Earth almost instantly, and when it finally reached the Alpha Centauri system, it would not gently drift in. It would flash through. The spacecraft would be moving far too fast to enter orbit around Proxima Centauri. It would not settle near a planet. It would not circle the star. It would not pause for a careful survey. It would race past the system and continue onward into deeper interstellar space. This is the hidden cost of the 20-year timeline. The speed that makes the journey possible also makes the arrival incredibly brief. If the probe passed near Proxima Centauri b, the possible rocky planet orbiting Proxima, it might have only minutes or hours to collect its most valuable observations. The exact time would depend on how close it passed and how its instruments were aimed. But compared with normal planetary missions, the flyby would be extremely fast. New Horizons passed Pluto at about 31,000 miles per hour. Even then, the closest approach was over quickly. The spacecraft had to take images and measurements on a carefully programmed schedule because there was no second chance. A starshot-style probe could be moving thousands of times faster than New Horizons was at Pluto. That makes every second precious. The cameras would need to point correctly. The sensors would need to activate at the right time. The onboard computer would need to know where it was. The probe would need to recognize its target after more than 20 years of travel. A tiny error in navigation could mean missing the planet by a huge distance. Across 4.24 light years, even a tiny aiming mistake can grow into millions of miles. And the probe would not have much fuel for corrections. The whole point of the concept is to keep the spacecraft extremely light. There is also the danger of the journey itself. Interstellar space is thin, but it is not empty. It contains individual hydrogen atoms, tiny dust grains, charged particles, magnetic fields. At normal spacecraft speeds, a speck of dust is a hazard. At a fraction of light speed, it becomes far more serious. A grain smaller than a sand particle could strike with enough energy to damage or destroy delicate parts of a tiny probe. The spacecraft would need to survive decades of exposure while moving through a medium we have only sampled directly with a few distant probes. Then, after surviving launch, acceleration, dust, radiation and navigation, it would face one more challenge. It would need to send its data home. That may be the hardest part of all. A gram-scale spacecraft cannot carry a large radio dish. It cannot carry a powerful transmitter like a deep space probe. It cannot carry a large nuclear power source. Any signal it sends would be faint, very faint, and Earth would be more than 4 light-years away. The signal would spread as it traveled. By the time it reached Earth, it would be weaker than almost anything we routinely detect. Giant receivers would need to listen carefully. The data might come slowly, a few images, a few measurements, a small scientific message from a machine that had already flown past the nearest star and was disappearing into the dark. This is why the light sail shortcut is both thrilling and humbling. It may offer a way for something built by humans to reach Alpha Centauri within a few decades, but that something would be tiny. It would arrive at enormous speed. It would stay for almost no time, and it would send back whatever it could before distance swallowed its signal. So the first fast answer does not fully solve the problem. It reveals a deeper distinction. Flying past Alpha Centauri is one achievement. Truly arriving, there is something else. This is where the word reach becomes slippery. A spacecraft can reach Alpha Centauri in more than one way. It can pass through the system, or it can truly arrive there. Those sound similar, but in spaceflight, they are completely different missions. A flyby is the simpler version. The spacecraft approaches the target. It takes images. It measures magnetic fields, particles, light, dust, atmosphere, or temperature. Then it keeps going. It does not stop. It does not orbit. It does not turn around for a second look. New Horizons did this at Pluto. It spent more than 9 years crossing the solar system. Then, on July 14, 2015, it swept past Pluto at about 31,000 miles per hour. The closest approach lasted only a short time. The spacecraft gathered its most important data during a carefully planned sequence. Then Pluto fell behind it forever. That mission still transformed our understanding of Pluto. But it was a flyby, a fast look, a once-only encounter. A light sail probe at Alpha Centauri would be an even more extreme version of that. At a significant fraction of light speed, it would not simply pass a planet quickly. It would tear through the system at a speed unlike anything used in planetary exploration. The useful observing window could be narrow. The spacecraft would have to do its work almost perfectly. There would be no chance to slow down, reposition, and try again. An arrival is different. An arrival means the spacecraft removes enough speed to stay. It might enter orbit around Proxima Centauri, It might orbit Proxima Centauri b. It might release smaller probes. It might map a planet over months or years. It might watch weather patterns. It might study flares from the star. It might search the atmosphere for gases that could hint at life, such as oxygen, methane, or carbon dioxide in unusual combinations. It might send a lander down if a solid surface was reachable. That kind of mission would be far more valuable scientifically. A flyby gives a glimpse. An orbiter gives time. A lander gives contact. The difference is enormous. At Mars, flybys came first. Mariner 4 flew past Mars in 1965 and returned the first close images of another planet. Those images showed a cratered surface and changed how people imagined Mars. But later orbiters revealed far more. They mapped valleys, volcanoes, ice, dust storms, and minerals. Landers and rovers added another layer by touching the surface directly. The same pattern would apply at Alpha Centauri. A flyby could prove the journey was possible. An orbiter could begin real exploration. A lander could turn a distant point of light into a place. So when asking how long it would take to reach Alpha Centauri, the answer depends on the meaning of reach. If reach means crossing into the star system and taking a brief look, a tiny light sail probe gives the shortest serious timeline. A little over 20 years for the crossing. Then, more than 4 years for the data to come back. If reach means arriving with enough control to stay, the timeline becomes harder. The spacecraft must bring more capability, more instruments, more power, more protection, and most importantly, some way to slow itself down. That changes everything, because a mission that only flies past can spend almost all its effort on speed. A mission that arrives must spend effort on speed and braking. The destination is not just a finish line. It becomes a place where the spacecraft has to survive, steer, and work. Alpha Centauri is close enough for a tiny probe to imagine crossing the gap. But arriving there in a useful way means solving the hidden half of the journey. Stopping. Stopping in space is stranger than it sounds. On Earth, stopping feels natural. A car slows down because its brakes press against the wheels. A plane slows down because air pushes against its wings and body. A boat slows down because water resists its motion. But in deep space, there is almost nothing to push against. No road, no air, no ocean. A spacecraft moving between stars keeps moving unless something changes its velocity. Velocity means speed in a direction. To arrive at Alpha Centauri and stay there, a spacecraft has to remove most of the velocity it spent years gaining. That is the hidden cost of arrival. If a probe crosses the distance at 20% of light speed, it is moving at about 134 million miles per hour. That speed is the reason the trip can take just over 20 years. But it is also the reason the probe cannot simply settle into orbit. Proxima Centauri's gravity would tug on it as it passed. The planet, Proxima Centauri b, might tug on it too. But at that speed, those gravitational pulls would be far too weak to capture it. The spacecraft would rush through the system like a bullet passing through a field. To stay, it has to slow down. And slowing down can be almost as hard as speeding up. This is because speed does not care which direction the engine points. If a spacecraft used a powerful engine to accelerate to interstellar speed, it would need a similar change in velocity to cancel that motion at the destination. A mission that accelerates for years may need to turn around and decelerate for years. The engine points backward at the beginning. Then, near the destination, the spacecraft flips. The engine points forward. The thrust now acts like a brake. That sounds simple in outline, but the fuel has to come from somewhere. If the spacecraft carries braking fuel, that fuel must be accelerated during the first half of the journey, so the spacecraft is heavier at launch. Because it is heavier, it needs more energy to reach speed. Because it needs more energy, it may need more fuel. The same trap returns. Even a robotic probe becomes difficult. A larger science craft becomes harder. A crewed ship becomes almost overwhelming. There are ways to imagine braking without carrying all the fuel. One idea is a magnetic sail. A magnetic sail could use a large loop of superconducting wire to create a magnetic field around the spacecraft. Superconducting means electricity can flow with almost no resistance if the material is kept extremely cold. The magnetic field could interact with charged particles streaming from a star. Those particles are called stellar wind. They are mostly protons and electrons moving outward from the star. As the spacecraft approaches Proxima Centauri, the magnetic sail might push against that flow and slowly bleed away speed. The problem is that stellar wind is thin. Red dwarf stars like Proxima can be active, but their wind is still a sparse stream of particles spread through space. The braking force would be gentle. It might take years. It might take decades. And the sail system would need to be huge, light, strong, and reliable after surviving the entire interstellar crossing. Another idea is to use light from the destination star. A reflective sail could turn toward Proxima Centauri and let starlight push against it. The pressure from light is real, but it is weak. To slow a spacecraft moving at a fraction of light speed, the sail would need to be extremely large and carefully controlled. It would also need to survive heat, radiation, dust damage, and the stress of unfolding far from Earth. A sail that works near our own star may behave very differently after decades in interstellar space. A third option is to aim for a flyby of Alpha Centauri A or Alpha Centauri B, using their brighter light and stronger gravity to help bend and slow the path. But those stars are arranged in motion. Their positions change. Their orbits are complex. The spacecraft would need astonishing navigation accuracy to use them safely. A small error could mean missing the braking opportunity entirely. So the deceleration problem changes the answer again. Getting to Alpha Centauri quickly is one challenge. Getting there slowly enough to study it is another. A flyby mission can spend its whole design chasing speed. An arrival mission must carry the burden of stopping. And if stopping is this hard for a probe, the difficulty grows far larger when the payload is alive. A probe can be small. A human mission cannot. The moment people are placed aboard a spacecraft, the journey changes completely. The payload is no longer just cameras, sensors, antennas, and computers. The payload is life. Humans need air every minute, water every day, food for years, warmth, light, sleep, medicine, privacy, movement, a way to stay calm while Earth falls farther and farther behind. A robotic probe can go silent and still complete part of its purpose. A human crew cannot. If the air system fails, the mission becomes an emergency within minutes. If the water recycling system fails, the timeline becomes days. If food production fails, the danger stretches across months. If radiation shielding is too weak, the damage can build slowly for years before anyone fully understands the cost. That is why a crewed Alpha Centauri mission would not look like a larger version of Voyager. It would be closer to a sealed world, a small artificial environment built to survive between stars. The International Space Station gives a tiny preview of this problem. It orbits only a few hundred miles above Earth. Astronauts can return home in hours if needed. Cargo ships bring supplies. Mission control watches constantly. Replacement parts can be launched from the ground. Even with all that support, the station needs careful life support systems. It recycles water from humidity, sweat, and urine. It removes carbon dioxide from the air. It needs regular maintenance. Astronauts exercise for about 2 hours each day to slow muscle loss and bone loss in weightlessness. Now stretch that idea across the distance to Alpha Centauri. No resupply, no emergency return, no spare rocket waiting nearby, no hospital, no fresh crew, no quick repair from Earth. Every filter, pump, valve, wire, seed, tool, and medicine package would have to be brought along, manufactured aboard, or replaced from stored materials. The ship would need food systems, perhaps hydroponic gardens where plants grow in nutrient-rich water instead of soil, perhaps algae tanks, perhaps carefully controlled crop rooms with artificial light. Those systems would need power, water, nutrients, backup pumps, backup lights, protection from mold, disease, and crop failure. A single garden failing would not be a small inconvenience. It could threaten the entire food supply. Radiation becomes another major burden. Earth protects life with an atmosphere and a magnetic field. Between stars, there is no planetary shield. High-energy particles, called cosmic rays, can pass through spacecraft walls and damage cells. Over a short mission, that risk can be managed. Over decades, it becomes part of the architecture. The ship would need shielding made from water, fuel, plastic, or other materials rich in hydrogen, because hydrogen can help slow some forms of radiation. But shielding is heavy, and every heavy layer has to be accelerated. Then there is gravity. A crew traveling for decades cannot simply float forever. Long periods of weightlessness weaken bones and muscles. One possible solution is rotation. A spinning section of the spacecraft could create artificial gravity by pushing people outward against the floor. But that requires a large structure. If the rotating section is too small, the spin can make people dizzy and sick. So, the ship grows again. More structure, more bearings, more cables, more maintenance, more mass. Psychology may be just as important as engineering. A crew would live inside the same metal world for years or decades. The same corridors, the same faces, the same recycled air, the same routines. Researchers study isolation in Antarctic stations, submarines, and space missions, but none of those fully match an interstellar voyage. A person on a ship to Alpha Centauri would know there is no outside world to step into, no weekend away, no rescue team close enough to arrive, no normal conversation with Earth once the delay grows into years. So a human mission becomes heavier in every sense. Physically heavier, emotionally heavier, scientifically heavier, ethically heavier. A tiny probe can be treated as a fast message thrown across the dark. a human ship has to carry a living piece of Earth with it. And once humans are aboard, the travel time is no longer just a number on a chart. It becomes the shape of an entire life. For a human mission, the dream number is 10% of light speed. That sounds small at first. Only 1/10. Only a fraction. But light moves so quickly that even 1/10 of that speed is almost beyond imagination. Light travels about 186,000 miles every second. 10% of that is about 18,600 miles every second. In 1 hour, a spacecraft moving that fast would travel about 67 million miles. That is roughly the distance from Earth to Mars during some favorable close approaches. In a single day, it would cross more than 1.6 billion miles. In a week, it would travel farther than the distance from our own star to Saturn. At that speed, Alpha Centauri finally begins to fit inside a human lifetime. Proxima Centauri is about 4.24 light-years away. So a spacecraft moving at 10% of light speed would take a little over 42 years to cross the distance. That number does something strange. It brings Alpha Centauri out of deep history. Voyager speed gave us tens of thousands of years. Parker speed gave us thousands of years. 10% of light speed gives us decades. Still long. Still severe, but suddenly possible to imagine inside a single life. A person could leave Earth at age 25. They could arrive in their late 60s. A person could leave at 30. They could arrive in their early 70s. The journey would consume nearly an entire adult life. Not a mission season. Not a temporary assignment. Not a few years away from home. A lifetime between stars. And even this clean number is generous. It assumes the spacecraft can quickly reach 10% of light speed, then hold that speed across the long dark gap, then somehow slow down at the destination. If acceleration and braking take years, the total mission becomes longer. If the ship accelerates gently to protect human bodies and the structure of the ship, the crossing becomes longer again. A human body can handle one Earth gravity comfortably, because that is what life evolved under. At one Earth gravity of steady acceleration, a ship would reach 10% of light speed in a little over a month. But keeping that acceleration would require a vast and continuous supply of energy. A gentler acceleration would be easier on the ship, but would stretch out the timeline. Even once the ship is moving, the environment becomes dangerous. At 10% of light speed, the spacecraft is not drifting peacefully. It is carving through interstellar space at extreme velocity. Hydrogen atoms would strike the front of the ship like radiation. Dust grains would become serious hazards. A grain smaller than a speck of sand could hit with enormous energy. The ship would need shielding at the front. That shielding would add mass. That mass would require more energy to accelerate, and the old problem would return. Inside the ship, 42 years would need to be survivable. People would grow older. Children might be born. Crew members might get sick. Systems would break. Food would need to grow. Water would need to cycle again and again. The same ship would have to remain home, workplace, hospital, farm, shelter, and world. Messages from Earth would slowly fall behind. After 1 light year, every message would take 1 year to arrive. Halfway to Alpha Centauri, a reply from Earth would take more than 4 years for a full exchange. By the end, Earth would be more than 4 years away by light. The crew would still hear from home, but home would arrive as history. 10% of light speed is the first answer that feels almost reachable for humans. It gives the dream version of the journey. A ship leaves Earth. A human lifetime passes. Another star fills the forward view. But this speed is far beyond any crude spacecraft humanity can build in 2026. No human vehicle has come close. No life support system has operated for 40 years without resupply. No Starship engine exists that can push a crude world to 67 million miles per hour. So the dream answer sharpens the honest one. Alpha Centauri can fit inside a lifetime only when the spacecraft belongs to a future we have not built yet. So the real answer has several layers. If humanity left in 2026 with proven spacecraft technology, Alpha Centauri would remain a journey of thousands to tens of thousands of years. At Voyager 1 speed, the trip would take roughly 70,000 to 80,000 years. At New Horizons style speed, the answer stays in the same broad range. At Parker Solar Probe's record speed, treated generously as a straight cruise through interstellar space, the trip still takes around 6,600 years. That is the best modern speed comparison, and it still places arrival far beyond any normal mission plan. A spacecraft leaving in 2026 at Parker, like speed, would arrive around the year 8,600. By then, the modern world would be ancient. The languages spoken at launch might be unreadable. Countries could have changed beyond recognition. Coastlines could have shifted. Records could have been lost. The spacecraft might arrive long after the society that launched it had become archaeology. That is what proven speed gives us. It gives movement. It gives distance. It gives escape from the solar system. But it does not give practical travel to the nearest star. Then there is the most optimistic tiny probe answer. A light sail concept could, in theory, send a gram-scale spacecraft toward Alpha Centauri at a significant fraction of light speed. If it reached about 20% of light speed, the crossing could take just over 20 years. Then the signal from the Flyby would need more than 4 years to return. That means people on Earth might receive data within a few decades. For the first time, Alpha Centauri enters a human time frame, but the cost is severe. The spacecraft would be tiny. It would carry only limited instruments. It would have very little power. It would likely pass through the system without stopping. It might have only a brief window to observe Proxima Centauri or any planet nearby. Then it would continue outward, farther into the dark, while its faint signal spread across more than 4 light-years. So the fast answer is real only for a very specific kind of mission. A small probe, a flyby, a brief glimpse, a tiny message sent home from another star system. That would still be one of the greatest achievements in human history. But it would not be the same as arriving. It would not be a crude journey. It would not be an orbiting observatory. It would not be a landing. It would be the first touch of the next star, more like throwing a needle across an ocean and hearing it whisper back. Then there is the human answer. For people to reach Alpha Centauri in a single lifetime, the spacecraft would need to move at something like 10% of light speed. That would make the trip a little over 40 years, before counting acceleration and braking. A person could leave Earth young and arrive old, but in 2026, no crude spacecraft can reach anything close to that speed. No life support system has kept humans alive for decades without resupply. No rotating starship has provided artificial gravity across an interstellar voyage. No shield has protected a crew from cosmic rays and dust impacts at a fraction of light speed. No engine exists that can push a living ship to 67 million miles per hour and then slow it down safely at another star. So the honest 2026 answer is humbling. With real spacecraft, Alpha Centauri is thousands to tens of thousands of years away. With the most ambitious tiny probe concepts, it may be a few decades away, but only as a fast flyby with enormous technical challenges. With humans, it belongs to a future level of engineering, a future of engines, materials, life support, shielding, and navigation we have not yet built. The numbers answer the original question, but they also reveal something deeper. Alpha Centauri is the closest star system, and still, it shows how early humanity is in the story of spaceflight. Alpha Centauri is the closest natural target beyond our own solar system. That is what makes it so powerful. It is close enough to name, close enough to measure, close enough to appear in sky maps, telescope studies, mission concepts, and serious scientific papers. It is close enough that light from Proxima Centauri reaches Earth in a little more than 4 years. And still, it is distant enough to humble every spacecraft humanity has ever built. That is the strange truth at the center of this journey. The nearest star is nearby only by the standards of the galaxy. By the standards of machines, bodies, engines, fuel, and time, it is still almost unimaginably far. A spacecraft like Voyager 1 gives us one version of the answer. Tens of thousands of years. A journey longer than agriculture, longer than cities, longer than written language, longer than every civilization that has ever risen on Earth. A spacecraft like New Horizons gives a similar lesson. It crossed the solar system quickly enough to make Pluto feel reachable. But the same speed becomes almost motionless when stretched across 25 trillion miles. Then Parker Solar Probe gives the fastest modern comparison. 430,000 miles per hour. The greatest speed ever reached by a human-made object. And even if that speed could somehow be aimed straight toward Alpha Centauri and carried across interstellar space, the trip would still take around 6,600 years. That is the best answer from proven speed. Thousands of years. A journey measured across the lifespan of cultures, languages, and entire eras of human history. The faster answers require stranger machines. Nuclear propulsion gives more power than chemical rockets. Fusion begins to feel like an engine worthy of the stars. Antimatter pushes toward the deepest energy stored inside matter itself, but each step adds difficulty. Radiation, heat, shielding, fuel storage, failure risk, engineering that has never been tested across the space between stars. Then the light sail shortcut changes the shape of the answer. A tiny probe, pushed by a powerful beam of light, might reach Alpha Centauri in just over 20 years. For the first time, the nearest star becomes a destination inside a human lifetime. But that answer comes with a trade. The probe is small because it must be fast. It can reach the system, but it may only fly through. A brief glimpse, a few measurements, a faint signal returning across more than 4 light years, a whisper from the edge of another stellar family. To truly arrive, the spacecraft must slow down, and stopping at another star can be as difficult as getting there. A flyby is a crossing. An arrival is a capture. An orbiter, a lander, or a crewed ship would need braking, power, shielding, navigation, and endurance on a scale far beyond a tiny probe. And if humans are aboard, the journey changes again. The spacecraft must carry a living piece of Earth, air, water, food, medicine, gravity, or something close to it. Protection from cosmic rays. A place for people to sleep, work, age, recover, and remain sane while Earth becomes years away by light. At 10% of light speed, the trip could take a little over 40 years. That is the first human-scale version of the journey. But it belongs to a future we have not built yet. No crewed ship in 2026 can travel at 67 million miles per hour. No human life support system has crossed decades without resupply. No engine has pushed a living world toward another star and then slowed it safely at the end. So the answer to the question is simple and also enormous. If humanity left in 2026 with real spacecraft technology, Alpha Centauri would take thousands to tens of thousands of years. If we sent a future tiny probe, it might take a few decades. If humans went, the journey would require a civilization that has learned how to build starships rather than spacecraft. And that is why Alpha Centauri matters. It gathers the whole problem of space travel into one place. Speed, energy, mass, fuel, dust, radiation, communication, survival, braking, time. The closest star system becomes a measuring stick. It shows how far we have come since the first rockets, and how far we still are from becoming a species that can move freely between stars. Alpha Centauri is real, a triple system in the southern sky. Two bright stars dancing together. One small red dwarf farther out. A possible rocky world circling in the dim red light. It is close enough to dream about. Close enough to aim toward. Close enough that someday something made by human hands may cross the dark and reach it. But for now, it remains just far enough to remind us how young we are. The nearest star is waiting, and the distance between here and there is still one of the greatest measurements of humanity itself.